Okay, so this is the third part of our attractor points sort of grid panel tutorial from last week. So just a quick run through of what we did. We ended up with a structure like this. We had sort of like a panel frame gridded structure around our revolved surface with a bunch of spikes on it that were influenced by the position of an attractor point. So the closer the spikes got to the attractor point, well, I guess the closer the attractor point got to the spikes, the longer the spikes were. The further away, the shorter they were. So this is the script that we had. It's quite a big script. So I went over it in the previous two tutorials, but this is just to do the Weaverbird stuff. But let me turn all that off for a second so you can see where we left off and how we got here. So I'll turn everything off. So essentially what we did was we created a revolved surface, right? So we used our initial geometry, our generatrix and our center curve. This is our center curve here, and this is our generatrix here. We basically used that with the revolve command to create this sort of funky quarter surface here. And we defined it as a quarter by going 0 to 90 degree domain. And then we divided it, and we shifted the matrix, just like we did in week 4, to create these panel boundaries. So that's how we did that, by essentially creating these in each of their separate lists, and then polylining them together. Or I guess in this case we lofted them together. Oh no, we did polyline them over here. Anyway, so that's how we got that kind of surface. Now you don't have to do a revolved surface, you can do any kind of surface. It'd actually be cool if you didn't do a revolved surface. Essentially all we're looking for is a panelized surface that morphs shape based on an attractor point. It doesn't even have to be spikes, it can be sort of like openings, like the panels themselves can sort of morph, open and close as they get closer to an attractor point. You could have some kind of like an iris kind of shape. I know some of you referenced the Star Tower in Dubai or in Bahrain or wherever it was, that has that sort of opening kinetic structure. Anyway, so we turned these into a mesh. So we have our, I'm going to call this just like a panel frame, because that's essentially what it is. What we essentially did here was we scaled and moved these panels so that they now have some thickness. So I'll show you what I mean by that. We have our internal cells, which are just scaled down from the initial panel boundary. We have our exterior frame, which was scaled outwards from the panel boundary. And then we have the interior frame, which was scaled inwards. And then essentially what we did was we merged them all together and lofted surfaces between these lines. So we got this sort of divoted shape here, which is eventually going to turn into our Weaverbird organic shape. So that was creating the panel frames. And then what we did down here was we created vectors for our spikes. So these are the vectors that we created for the spikes. You guys have, if you're watching this video, you're probably already up to this part, so that's totally fine. Don't need to go into it anymore. So these are all the vectors. This is the list organization for our spikes. This is moving them based on their proximity to that attractor point down here. And we ended up with our spikes looking like this, which is just sort of like you can think of this as like a facade that goes on top of the frame panels. So you can see how, based on the proximity to the attractor point, these ones are longer and these ones are shorter. That's all we're looking for this assessment. We're just looking for some kind of geometry that changes shape relative to an attractor point. So if you look at Daniel's tutorial, he shows it quite nicely. Branko's tutorial does it as well. Then there's plenty of tutorials on YouTube that show how to like wire up an attractor point kind of setup. It's one of the more sort of key aspects of doing parametric design in Grasshopper. It doesn't really matter what kind of surface you go for. Obviously we went for the revolved surface. You can use any kind of surface that you create. I would recommend, if you want to pick like an existing building or a conceptual building that you like, and just sort of approximate the geometry of it and then subdivide it. If you can do that in a similar way to how we subdivided ours up here, then you'll turn out with this panelized frame, and then all you have to do there is sort of add something at the intersection points or add something at the center points that scales based on the attractor point. Just think outside the box, and don't copy exactly what we've done in the tutorial. I know this one's a little bit trickier to do sort of your own iteration for, but you really can't go wrong if you follow those steps, which is just create a surface, panelize it, and then at various points on the surface create sort of geometric elements that scale based on this attractor point script. This kind of script you can adapt to any surface. This doesn't have to just be for our revolved spiky surface. Okay, so anyway, we'll move on to the Weaverbird stuff. So we have our frame panels, which is this frame. We have our spikes, which is the spikes. What we need to do, essentially what we're going to do is this is just a quarter slice of our total geometry. We're just going to mirror it a couple of times across different planes so that we get our full 360 degrees. Now, we didn't do this earlier because it would be a little bit too computationally demanding to render, I guess, 4 of these. So it's a little bit quicker for our tutorial to just show a quarter of it and then, you know, like multiply a quarter of it. The other thing is that our attractor point moving around our revolved surface means that at some point there's going to be a part of the surface that is directly opposite the attractor point. So if you can imagine, there's like a circle around the surface and the attractor point moves around that circle. We tried to avoid having sort of like inverse vectors, so that would pull the spikes inwards instead. That was just for this particular geometry. With yours, you can do whatever you want as long as you use an attractor point on a panelized surface. So first thing we're going to do is we're going to do the exact same process to each of these. We'll space them out a little bit. We are going to weld mesh. Basically what this does is it simplifies the mesh so that it's a little less intense. So you can see we have one mesh with 1,216 vertices and 304 faces. Now if we meld that together, it becomes 246 vertices and 304 faces. So it's essentially what it does is it keeps the number of faces, but it joins duplicate vertices. So it simplifies the mesh a little bit. So that's good. That makes it a little less hard for the computer to render. So essentially what we're going to do is mirror it now using the mirror command. Now if we mirror it, it's going to pop it onto that side, which is good. But we also want to specify the plane that we want to mirror it on. So let's say the XZ plane is probably the first one that we want to start with. So we'll start with that. Now this does it automatically pretty well, but if you want to specify where the origin point is, if let's say your structure isn't actually on the origin point, then that goes in there. So that's the origin of your plane. Ours is conveniently already at 0, 0, 0, so that's fine. We'll leave it there. But what we want to do next is mirror that again. So we have this half of our total circle. Now if we mirror this half, we're going to just get the other half, right? So we don't have to do 4 of these individually. So we're going to mirror this and mirror that, and there are our 4 segments. So now we should have, this one contains the half, this one contains 2 quarters, and we'll just leave it like that. So just to clarify, this is on the YZ plane. So if you have a look at this little, down here, this little sort of axes map, the ZX plane, as you can imagine, this sort of cuts a line through our surface like that. And then this one is the YZ plane, so it cuts a line through our surface like that. This is the plane that the mirroring is happening on. Anyway, so next we're going to merge. So the first thing we want to do is plug our original weld into the merge. And then our second one goes into the merge, and our third one goes into the merge. So this essentially just gives us our full 360 degrees, right? Kind of looks like a bird cage. So if you've got a different surface, like a surface that doesn't sort of correspond to this, you may not even need to do this step. But if you're using a revolve surface, then this is what you do. This is obviously this last sort of mirror process really depends on what your surface is. So if you need to mirror it, then mirror it. If you don't, then don't. All you need is really a panelized surface. It doesn't have to be this sort of 360 degree cage looking thing. Next thing we're going to do is join our mesh together. So mesh join, just like that. I'm going to turn off the display for all of these because we've already got what we want there in our mesh join. Now it's time for the Weaverbird stuff. So before we use a Weaverbird command, we need to use Weaverbird's built-in join meshes and weld, which does a bit of a better job welding our meshes together than the initial default mesh weld. So we're going to type in Weaverbirds, Weaverbirds join meshes and weld. Yeah, so it looks like this. So we'll join that in there. Great, that works. So this is our mesh input, mesh output, and this is weld. So what does this say? Indicates if the coincident points of mesh face should be joined after the union. Now, do we want that to be false or true? Let's have a quick look. No, we'll keep it false. Okay, cool. All right, so next part is what is going to generate our organic kind of looking thing. Great way of explaining it. It's called the Catmull-Clark subdivision. This is sort of a mathematical subdivision that's based on some guy in the 80s writing some kind of thesis. Anyway, we don't really care about that. We want to figure out, we want to make it look pretty. So we'll just plug the mesh into there. So now you can see, if I turn off all of this stuff, you can see that it has made our mesh a little bit more organic. So whereas before we had square holes, now we've got these sort of more rounded holes. And if we turn up the number of levels, so I'll just make this go from 0 to 10, just for simplicity, we can see the fidelity start to increase. Yeah, so have a look at the holes while I'm doing this. They're getting more and more complex, up to a certain point. It seems like maybe 3 is probably the maximum. If I go to 4, it sort of goes back down. So we'll keep it at 3. Level 3 seems good. So now this has turned into a really nice looking organic mesh. So this is one of the requirements for the assignment as well. If you're using, I think it was, if you were using Citrix, I don't think you can install plugins. So if anyone has trouble, so for Citrix users, you'd want to install your own copy of Rhino onto your computer. If you're having problems with that, just email me and I can see what I can do. Because I know that Rhino has started to sort of shut down any unauthorized attempts. If you've got the spare cash for it, I would recommend buying Rhino. But I mean, I'm a bit of a hypocrite because I still haven't done that yet. Anyway, so that's done. There's our Catmull-Clark subdivision. And if you want to give it a color, we can go into color swatch. So a swatch is essentially just, I guess it's a color. It's like an input, but a color. And then we use color, what do we use? Hang on, what is it called? Custom preview, that's what it's called. Tip of my tongue. All right, custom preview. So that'll let us apply a color to our geometry. So custom preview. You can use it for materials, line weights, or colors. We're going to just use colors. So I plug this in here, then that'll give us a nice bright white, which we don't want because that's kind of lame. So let's pick I don't know what looks cool. Yeah, purple's kind of cool. So this will give us a sort of better representation of our geometry than the traditional sort of red preview. So yeah, that's the Weaverbird stuff done. It was all pretty simple. Essentially, all Weaverbird did was allow us to join meshes in a better way and use this Catmull-Clark subdivision. There's also a different kind of subdivision that wasn't in the tutorial that I'll show you called, I think, the loop subdivision. Let's see if this looks any different. So if I plug this in here, like that, we'll see the kind of differences there. Let me give the loop a blue swatch, and let me give the Catmull-Clark a red swatch so that we can see the difference. Then I'll turn off the Catmull-Clark and the custom preview. So I kind of see the difference here. So loop looks like it doesn't panelize it doesn't turn the meshes into quads, it turns them into tris instead. So you can see that every sort of individual element here is a triangle. Whereas if I turn this off and then turn on custom preview for this, you can see that every element here is a quad. So I guess it's personal preference which one you want to use. The tutorial used Catmull-Clark because I think quads are generally easier to work with if we're doing sort of mesh manipulation, but we're not. So do whatever you want, I guess. So it's either quads or tris. Doesn't really bother me which one you choose. I think for this kind of geometry, they have the same effect. Tris might be a little bit more organic looking because it's harder to approximate a square surface with triangles at sort of a lower level of detail. But whatever looks best on your model is totally fine, as long as you use one of the two. So either one of those is fine. All right, so essentially we've created our cage around the edge here. Actually, let's turn off that and turn that back on. There we go. That's what we're kind of supposed to be working with. I'll give this a bit of a nicer color as well. There, that's a little bit softer. Okay, so essentially, we'll do the exact same thing, like literally the exact same thing for the spikes. So we can just copy all of this. So select it all and then Control C, Control V, or Command C, Command V. And then if we just swap out the input for the mesh, then we have spikes all over it. And I'll change the color so that it's a little bit more obvious. So there's our spikes. And then if I turn off this, so essentially what we ended up here with is these kind of rounded off, softened spikes on the surface of our rounded off, softened frame. So yeah, that's pretty much it. You can see we've got this this really neat sort of organic shape. Looks kind of like a sea creature or something, or a pine cone. But if we change our attractor point, this will have to happen very slowly because it will redo the mesh calculation as well. But you can see, you know, the spikes grow as the attractor point nears the top, and then if I move it down to the bottom, the spikes grow down the bottom. So this is a kind of really neat parametric design that could help you design interesting organic facades, or any other kind of, you know, sculptural installation, something like that. Yeah, so this kind of method can apply to any surface really. So yeah, just experiment with it. Try and find new ways to subdivide the surfaces, because not all surfaces are going to subdivide in the same way. Essentially, all you need is just a grid like this, and a grid that's given some thickness as well. You'll find ways to do that just by typing in, you know, like grid commands or contour commands or some kind of subdivision or quad paneling thing. There's a really good, actually this is probably important, this will help a lot of people. There's a really good plugin called Lunchbox, which is up here. Essentially, it takes surfaces and B-reps, and it just panelizes them like in one component. So if I was to sort of turn all of this off, so what I'll do is I'll just hit the turn off button there, and this is just an experiment, but we've got our base surface here, right, that we started with. If I use Lunchbox, which you can find just by Googling Lunchbox Grasshopper installation and following the steps to install it, and I go and I use the quad panels component, plugging it in here, you can see we've essentially got a similar output to what we had before. Right, so whereas before we had a kind of more rigid panel, this one you can define the U, so the U and the V is essentially just how many subdivisions it is across the X and Y dimensions, or horizontal and vertical dimensions. So this is probably a quicker way of doing it. Lunchbox has some other cool components like creating like braced structures, so these are like trusses almost. So if I take this like grid structure thing and then plug it in there, you can see we've essentially got our, our panels, lines and nodes all ready to go. Now, it is important, while we were doing our script in here in previous classes, we had each of our panels sort of in their own branch of a tree. So each panel, you could select it individually if you used a list item, whereas I'm not sure if it does that for this. That's going to be something you'll have to play around with. But yeah, this should be a bit of an easier way to do it. So I'm just looking at some of these now. I haven't used this that much before, but yeah, you can panelize it into triangles. That's kind of cool. Yeah, that's neat. Yeah, so at all of these intersection points, you could potentially put some of your own geometry. Oh yeah, that does look really cool. Huh. Okay. Yeah. Cool. So Lunchbox is a cool command. Plugin that you can use. Yeah, I wouldn't be opposed to you guys using this as a sort of shortcut to get to the panelization that you need to achieve for this kind of setup. Yeah, that's an interesting surface. So with Lunchbox, you should feel a little bit more confident to create any kind of surface geometry that you want and then panelize it. It sort of takes the hard work out of it. But yeah, remember to organize your lists in a similar way to what we did in tutorial. So that's going to be one of the main issues with this, using this shortcut, is that by sort of skipping a couple of steps and creating this nice panel structure, you'll also skip the list organization that we needed to get our rows in the right place and our trees in the right sort of branch structure. So just make sure that however you're manipulating these panels, you're able to, when you plug a list item in, so I don't think we're going to get it here, but when you plug a list item in here, you get each individual panel. So if I do that, then turn that off. Okay, yeah, no, so we do get a panel. But I think the problem with this one is that you're going to have to kind of deconstruct, I guess, yeah, deconstruct a mesh face. You're going to have to find a way to deconstruct each of these panels into their respective sort of segments and their vertices. Just carefully look through the script and see how our segments and our vertices from our initial panelization that didn't use Lunchbox, how that works. But yeah, you can use Lunchbox and then the deconstruct brep component. And I think what that should do is give you the faces. So if I go to list item, just to see if we're going the right direction, and then put in a slider from like 0 to 100, because maybe there's 100 faces, I guess, and turn that off. So yeah, so if I guess I'll flatten this. Yeah, so this would be a good way of selecting the individual faces. So you can see I've got the faces. I'm able to select them individually. And if I plug in the edges, I can select those individually as well, but that's a little less, a little less intuitive. Yeah, it's a little more complicated. So yeah, just be careful with how your lists are organized with this one. But yeah, deconstruct brep might be what you want, or there might be a component in here that I'm missing that helps you isolate individual faces. But yeah, Lunchbox is a good shortcut to panelizing sort of different surfaces that sort of that aren't revolved surfaces. So yeah, get creative with the kind of surface that you use. It'd be cool if it was inspired by something that another designer has done, or if it's something that you've done that you're happy with, go for it. Just try and avoid sort of this simple revolved line around an axis kind of thing that we covered in our tutorial. Try and get a little bit more creative than that. Yeah, so just to recap what we went over, we added sorry, I'll turn all this back on. It'll take a minute. So we meshified and welded all of our meshes together. We mirrored them so that they created that full 360 degrees. That won't apply to some of your surfaces, but for those who are doing a revolved surface, it kind of applies. And then we used Weaverbird's join and either one of these Weaverbird subdivisions to create our meshes. And I showed you guys Lunchbox, which you can find online by just looking up Lunchbox Grasshopper, so that'll help you panelize it if your surface isn't really panelizing the same way that we did it before. I think that's pretty much it. So yeah, so that's pretty much it. Week 7 is next week. That's when your stuff is due. So you'll have a poster for this due. Same sort of method that you used to do the posters for the previous assignment. Except this time you need 3 unique variations, and then you'll also need the waffle script and the waffle poster and either the waffle model or the waffle render from Daniel's tutorial on Moodle. So under week 6, Daniel's put up a great tutorial for how to create a waffle structure. That is your task 2.3. This is your task 2.2, and task 2.1 was what was it? It was like that interweaving sort of list chicken wire looking thing on top of a surface. So that one was supposed to be 3D printed, but you guys can make a render of it if you don't have time to 3D print. Just make sure the renders are like professional-ish quality. I know a couple of people were just taking screenshots of like the viewport here. That's not really cutting it. You can either use the renderer that's built into Rhino, or I would prefer if you guys use Blender. It's not super difficult, and once you have the necessary setup, you can use it for all of your renders. So I would take the time to learn how to do like a really simple studio render of an object in Blender, and then you can apply that sort of technique to any of your objects that you need to render. Yeah, no, that's it. Yeah, so do your posters for 2.1, 2.2, and 2.3. And remember to submit your scripts as well alongside your posters. Was there anything else? I don't think so. If I think of anything else, I'll email it to you guys. All right. See you next week.